Welcome to week 3 lecture 5 of our course Introduction to Cryptology. In this lecture we will review the concepts that we have already studied and solve some examples. So, the first concept that we review is Legendre symbol. So, we see that if P is an odd prime and if A is any integer, then the Legendre symbol A by P is defined as follows: A by P equal to 0 if A is congruent to 0 mod P, A by P is 1 if A is a quadratic residue mod P, and A by P is minus 1 if A is a quadratic non-residue mod P. And Jacobi symbol is defined in this way: if n has factorization product p I raised to the power e I running from 1 to k, then the Jacobi symbol of A mod n is defined as a product of the individual Legendre symbols raised to respective powers. Now, let us look at Solovay-Strassen algorithm. Now, in this algorithm our goal is to decide whether n is a prime number or not. So, the input is an odd prime and the algorithm goes in this way that we choose a random integer a between a and n minus 1 and then calculate the Jacobi symbol for it. So, this is Jacobi symbol a by n, we store it in x. If the Jacobi symbol turns out to be 0, then we say that the number is composite. If it is not 0, then we calculate a raised to the power n minus 1 by 2 mod n and store it in y. Then we check whether x and y are congruent modulo n or not. If congruent mod n, we say that the number n is prime, otherwise not. Now, let us look at this example. Now, suppose that a Solovay-Strassen algorithm is executed with input 561 and the random integer chosen is a equal to 2, then what is the output? Okay. So, to calculate the output we have to calculate two things: the Jacobi symbol 2 by 561 mod 561 and also calculate, there is a misprint here, we have to calculate this, n is 561. So, a is 2 here, so I have to calculate 561 minus 1 divided by 2 mod 561. There is a slight error over here, so let us neglect that. Now, calculating the Jacobi symbol 2 by 561. Now, at this point we see that to calculate Jacobi symbol we do not have to calculate the factorization of 561, we can simply neglect that and we have to only calculate we can use the properties of the Jacobi symbol. So, we check that it is a second property. So, here the numerator is 2, denominator is 561. So, in the second property we see that 2 by n is 1 if n is plus minus 1 mod 8 and 2 by n is minus 1 if n is plus minus 3 mod n. So, we have to basically check whether 561 is plus minus 1 mod 8 or plus minus 3 mod 8. If we divide 561 by 8, then we see that the remainder is 1. Therefore, 561 is congruent to plus 1 mod 8, and therefore, this value is 1. On the other hand, we have to calculate, let us look at the algorithm, a raised to the power n minus 1 by 2. Here n is 561. So, neglecting the misprint over here, we have to calculate 2 raised to the power 561 minus 1 by 2. That means we have to calculate 2 raised to the power 560 by 2, that is equal to 2 raised to the power 280, and reduce it modulo 561. We can do that by using a calculator, and we will see that it comes to be 1. Thus, we see that 2 by 561 is equal to 2 to the power 561 minus 1 divided by 2 modulo 561. That means that this pair 2 and 561 satisfies this condition, and that is why the Solovay-Strassen algorithm will return 561 is a prime, although it is absolutely clear that 561 is not a prime. When we have such a situation, then there is a name for the positive integers which are decided as primes based on certain choice of A by using Solovay-Strassen algorithm. These integers are called Euler pseudo primes to the corresponding base. So, in the case of 561 and the choice 2, we will say that 561 is an Euler pseudo prime to the base 2. We have seen during our lectures that there is another pair 91, here again 91 is not Euler pseudo prime to base 2 is not sure, it is 10, it should be written as 10. So, similarly we have seen during our lectures that 91 is Euler pseudo prime to base 10. Because you can check that 10 by 91 is equal to 10 to the power 45 modulo 91. This is something that we have done in our lectures. Now, let us look at another problem. This is a problem related to computation of Jacobi symbols. Suppose we have got two numbers 610 and 987, and we would like to know the value of the Jacobi symbol 610 by 987. So, we will take this strategy, we will use the rules that we have already studied. So, let us see how to use them. We start from this point 610 and 987. We note that 610 is even and 305 into 2 is 610. Therefore, we note that it will split in this way. Two into 305 and in the denominator 987. So, using the third law, we will have 2 by 987 and 305 by 987. Now, we ask the question that what is the value of n mod 8, that is 987 mod 8. Let us find it out. 987 divided by 8 it is 3. So, we see that 987 is congruent to 3 mod 8. Therefore, we go to the second line of the second law. So, 2 by 987 is going to be a minus 1. So, we have 305 987. Now, we have found that 987 mod is 8. So, 987. So, let us see what to do with this. Now, we see that 305 is odd and 987 is also odd. So, we can directly use this reciprocity law, but we have to check which of these rules are satisfied by 987 and 305. So, we divide 305 by 4. So, we have 28 and 2. So, we see that we get 1. So, therefore, 305 is congruent to 1 mod 4. So, 305 is not congruent to 3 mod 4. So, therefore, we come to this case, and therefore, I know that I can switch over without change of sign, and that is what we are doing now. I will write 987 305, and now we will use the first law to reduce 987 modulo 305. Let us do that. So, it is 72. So, we will write 72 by 305, and now let us consider 72. We see that 72 is an even number, and therefore, we can divide by 2. So, we know that 8 into 9 is 72. Therefore, we have 2 cube into 9 by 305, and then using the third rule I can write minus 2 by 305 whole cube 9 by 305. All right. Now, I ask a question, what is the value of this? For that again we have to divide 305 by 8. It is 1. So, we see that 305 is congruent to 1 mod 8. So, we come over here. So, we know that it is 1. So, we have minus 1, this is 1, 9 by 305. Now, we know that 305 is not congruent to 3 mod 4, then we can again flip by using the third law. So, we will get minus 1 305 by 9, that is what we get there. And now, let us reduce 305 modulo 9. So, so I will get minus 1 minus 8 by 9 here, and this is minus of minus 2 by 9 whole cube 1 by 9, and of course 9 is 1 mod 8. So, this is 1. So, I will have minus 1 by 9, and 1 by 9 is 1. So, I have minus 1. So, that is the answer. So, this problem requires computation, but in some ways this is amazing that without factorizing we can get information related to somehow some information whose definition of some quantities whose definition involves factorization. So, this is interesting. Now, the last problem, this is an algorithm that we have done in one of our previous lectures, and this is called square and multiply algorithm. And this algorithm is a fundamental algorithm that is required for practical effectiveness of RSA, because in the RSA we need exponentiation of large numbers by large numbers. But the problem is that if we cannot do the exponentiation efficiently, then we cannot work with RSA. This algorithm ensures that we can do the required exponentiations efficiently. Now, let us see how to do that. Now, let us recall the algorithm first. we want to compute x raised to the power b mod n, where b is a very large number. And so, what do? We take b and we write the binary representation of b. We will see how to do that, and then we do something, that is, first we set z to 1, that is 1 is placed in z, and then we go into a loop, and the loop depends on the length of b, and it kind of comes down stepwise, and at each step I square z and then I check whether the corresponding coefficient in the representation of b is 1. If it is 1, we multiply x to the current value of z and put in z and then go back into the loop. If it is not 1, we do not do anything, we go back into the loop, square z and come and again go into the loop. Now, what we will do in this case is that we will take b equal to 13, which is small, and x equal to 7, and see how this algorithm works. All right. So, we have x equal to 7 and b equal to 13. 13 can be written as 1 times 2 cube plus 1 times 2 square plus 0 times 2 plus 1. So, this is B3, this is B2, this is B1 and this is B0. This is L minus 1, L minus 2 and so on, and this is B0, 1 and 0 in my general algorithm. So, in the beginning z is equal to 1, I go in, always remember that it is square and multiply, not multiply and square. So, we first square, if we square 1, it remains as 1, then I go in. So, let me write it over there. So, I start with z equal to 1, I go in, I squaring step. So, I am basically putting, after squaring, z is squaring, z is 1, I go into the loop. What do I see? After z squaring, I have basically gone into the loop, I go into a conditional, I see whether bi equal to 1 or not, and I start from L minus 1. In my case L minus 1 is 3. So, when I look at it, I say that B3 is 1, yes, B3 is equal to 1. Since B3 is equal to 1, the z will be updated to 1 into 7, because x is equal to 7. So, I get 7, and then I go back again to the squaring place. Now, if I go back again to the squaring place, my z is 7, if I square 7, what happens? We get 7 square. I am not writing the integer values, I am writing in terms of squares, so that we understand what happens. So, we come here. So, now I shift over here. So, my z is equal to 7 square, I go in again. So, I am essentially over here, I am now looping. So, once I am over here, so I am asking a question, I has come down one step. So, I am asking a question whether B2 equal to 1 or not, B2 equal to 1. Since it is 1, I go into that if statement. So, z is updated to 7 square into 7. So, that is 7 cube. I move up again to the squaring place, because I am not still exhausted of I, because I has only come down to 2. So, now I comes down to 1. So, I am over here now my z was 7 cube, I am squaring z, 7 cube square is 7 raised to the power 6, and I am going down again inside the loop, and I am asking a question whether b 1 is equal to 1 or not. B 1 is not equal to 1, so I do not do anything. I do not do anything, I move again back to the squaring step. Once I move back again to the squaring step, I have 7 to the power 6 in my hand. So, here when z goes up, z is 7 to the power 6. When I come to 7 to the power 6, I square again, 7 to the power 6 square is 7 to the power 12, and now I go again, I ask the question whether b 0 is equal to 1 or not. B 0 is 1 over here. So, z is updated to 7 to the power 12 into 7, which is equal to 7 to the power 13, and I am at 0. So, I go no further down, and therefore, my return 7 to the power 13. Now, in actual reality of the algorithm, what we are going to do is at each step we are going to reduce the result modulo n, and we are actually going to calculate the product. But I have not done that to show that how the exponent is taking care of itself and the final value is coming to the required exponent. So, that is square and multiply algorithm. We will have some more examples of square and multiply algorithm in the assignments, and this is the end of today's lecture.